Thank you for joining us this evening. You were brought into this session with your microphone and video off. If you have questions, please put them in the chat. Megan will kindly collect them and address them to Sean after his presentation. The program will be recorded and will be made available on the Detroit Public Library YouTube channel and through Wayne State University's website. I am masked because I'm in a semi-public area of the library. My name is Jennifer Dye. I'm a librarian at Detroit Public Library. We've had astronomy programs for several years now. Before the upheavals of 2020, we'd had in-person programs. And then we put programs on hiatus and eventually launched the Zoom programs. We started recording them last year. And over the last several months, we've been working with Megan McCullen, the director of the Wayne State University Planetarium. She helps me greatly with the Zoom programs, and she's provided a link to the community of Wayne State University faculty and alumni, include Sean in that. I'd like to ask Megan to speak briefly before I introduce tonight's speaker.
Thanks, Jennifer, and thank you, Dr. Gavin, for being here also. But thank you, Jennifer, for making this happen every month. We are back to having public planetarium shows at the Wayne State Planetarium on most Friday nights. I'll post some links in the chat if you're interested in those in-person shows in Detroit. And we also are participating again this year in Noel Night, which is coming up this Saturday for those of you who are from the Metro Detroit area. It's a big Midtown event with all sorts of happenings at the museums and churches and shops all throughout the area. So we will be doing planetarium shows this Saturday as well. So definitely check the Noel Night links to see all of the events that are going on there. And starting in January, I think we'll be able to increase our numbers on campus and be starting to do some lectures in person too. So stay tuned, and thanks for joining us tonight.
Yes, thank you. Dr. Sean Gavin, Associate Chair of the Department of Physics and Astronomy at WSU, will tell us about the disagreements about what science proved about the age of the sun in the early 19th century.
Well, thanks. Thanks for introducing me. My name is Sean Gavin. My pronouns are he, him, and I'm going to talk about a battle between, well, first I have to turn on my PowerPoint, because if I don't do that, then you're not going to know what I'm talking about. So I hope everybody can see that. You're getting my subtitles.
Several people who attend prefer to have the transcript.
Excellent, excellent.
Yes.
Thank you. Thanks for doing that. And so, so I'm going to talk about a battle between Charles Darwin and Lord Kelvin that led eventually to the idea that cosmology should be a science. And I'm a physicist. I'm not a historian. I'm not a biologist. And I'm not really even an astronomer. I just know about astrophysics from, the courses that I'm teaching. And so what got me into this was that I was interested in how scientists do science, and how the fact that how their characters play a role in how science is done, because they are kind of a bunch of oddballs, and these guys are that I'm talking about today are really exceptional oddballs. They're kind of real interesting individuals. So let's start with Charles Darwin. He was born in 1809. He was recognized as a very smart lad in his youth, and started studying natural history And he took off on his famous voyage of the Beagle in 1831 to 1836. And from there, the idea of natural selection took hold. And he ended up publishing his papers in 1850 and 58 at the same time as Wallace came up independently with the idea of natural selection. But Darwin's work was much more comprehensive, and he really pushed it as far as he could at the time in his On the Origin of Species and later work. Now, you can see in this picture that also the migration of the hair over the course of from the top of his head down to the bottom. It's, you know, kind of a common thing among people, and you know, it's also part of our presentation that this sort of thing takes place. Now, his idea of evolution was that similar species probably have a common ancestor, which could be extinct, and that their differences come about through gradual process. And his mechanism for this is natural selection. And this is really one of the big ideas that underlies all of modern biology. You know, the idea that you can have different birds separated in different parts of the Galapagos Island because they eat different stuff over the course of the years. They develop different beaks and different musculature and everything. Now, people have done experiments to demonstrate evolution, and you know, the one I show here is famous one with fruit flies, where they fed them different material, separated them in different fish tanks, and after a while, they could no longer reproduce with each other. Their mating preference, they became so different from each other from eating these different materials that, but you know, I don't have to tell anybody in the world today about evolution because we've all been seeing it with, you know, COVID. You know, they have the Omicron, and now I don't know where we are because I'm, you know, too terrified to keep following it. And you know, but you know, you see right before your eyes the evolution of these tiny little things. Now, in humans or big animals, evolution takes a lot longer. And, you know, for example, the trait of lactose tolerance evolved in Europeans over the course of, you know, 20,000 years. And the fossil record has shown that even much bigger changes could take place over the course of millions of years. And so geologists at the time of Darwin thought that the Earth is extremely old. They saw evidence of geological forces operating over vast timescales in the geological record, and they were beginning to unearth the bones of dinosaurs in England and other places. They found the iguanodon. This is a picture in the background of an iguanodon. Some of it in 1820s. This is all right at the time when Darwin is basically a young person trying to get into the business. And in fact, the idea of geology was one of the popular ideas was called uniformitarianism. The idea that basically the Earth is infinitely old, essentially for practical intents and purposes, infinitely old. And that the natural processes of volcanism, sedimentation, and erosion just move stuff around slowly over the time. But they saw no evidence of timescale. And Darwin's friends and teachers, including Charles Lyell, who wrote the famous book Principles of Geology, were big champions of this uniformitarianism. Now, when Darwin came up with his theory of evolution, he realized that it required a really long time to take place. to go from an iguanodon to, you know, a buffalo or a cow in the English countryside. Now, in the origin, he was conscious of that this time was needed, so he tried to come up with evidence to support his timescales. And so in the origin, he looked at this region in England called the Weald, which is south of London. It's got these features that look like layers should be there, but that the tops of the layers have been eroded away. And so he estimated the time for that erosion to take 300 million years. And he said, great, there's plenty of time for evolution to take place. And, you know, here's the thing about Darwin that you need to know, okay? Darwin was not really good at math, okay? He had a problem with math. He was really good at a lot of stuff. He's obviously, I don't know what you call a genius, but, you know, his mathematical skills were not that great. And so he was off by a factor of 10 in his estimation of the age of the Weald. And it kind of got him into trouble. And he was self-conscious about his ability in math, and that got him into more trouble. So here we come to our problem, our main battle of the beards. Okay, there's Charles Darwin on the one side said that evolution may take a lot of time, but geologists agree that the Earth is very old. On the other side was Lord Kelvin, the most vocal proponent of this point of view. He said that, well, look, this is baloney. I mean, physics limits the age of the sun and the Earth. You're just wrong about this evolution stuff. Okay, so who's Lord Kelvin? Lord Kelvin, somewhat younger than Darwin. He was born in Belfast. William Thompson is his name, and he he was very precocious. By the age of 16, he published 12 papers, and he was illustrious chair natural philosophy in the University of Glasgow. He invented the Kelvin scale of absolute temperature in 1848. So if you've heard of him, you've probably heard of that. He also came up with the concept of absolute zero and the second law of thermodynamics and a bunch of other things that are known in science. He was also known at the time as a worker in the Industrial Revolution, and he was responsible for laying the transatlantic telegraph cable, and for that he acquired great wealth, and he became Baron Kelvin because Kelvin is the river that goes behind his office in the University of Glasgow. Okay. But he was incredibly famous. This is the thing you need to know about him. He was incredibly famous. He was so famous as a scientist, as a thinker, as an industrialist, that he was buried in Westminster Abbey next to Sir Isaac Newton. Okay, he was held in that kind of esteem. So when a guy like that goes after Charles Darwin, Darwin is extremely nervous. Okay, so here's what a bunch of things Kelvin did. Kelvin invented and proved Stokes Theorem. Oh, don't ask. I mean, in science, things are invented all the time and other people get named after them. But anyway, he invented and proved this theorem. And here you're just supposed to look at this equation right here and say, whoa, smart guy, okay? He also invented a lot of things in the theory of electromagnetism, which was coming out at the time. And then also in fluid mechanics, a lot of mathematics he was known for. But as I mentioned, he was most well known among the popular community in England as for building the for laying the first transcontinental telegraph cable. And but physicists and chemists know him probably best because of his work on the second law of thermodynamics. The first law of thermodynamics basically says that energy in all of its forms are conserved. And this was important in Kelvin's day because at that time they were having the Industrial Revolution. So steam engines were doing a lot. Trains powered by steam were doing a lot. And they were trying to understand how to make better engines. So Kelvin came in with the second law when he realized that some of the heat that's used to drive a steam engine has to be expelled as waste heat in the form of exhaust. Okay, in order for the process to repeat in a cycle, some of it has to go out in exhaust. And prove that. And this says not only that energy is conserved, but basically you can't even break even in running a mechanical engine. And this is what set, oh yeah, that's right, sorry. So Kelvin was so famous that there's a refrigerator named the Kelvinator and a company that was founded in Detroit in 1914. This is an actual photograph of a Kelvinator refrigerator. It's shined up nicely. And you can see, that's how famous he is. He's a really famous guy. So Kelvin turned his mind to the age of the sun and the earth, and he realized that they had to have limited lifetimes. He said, because thermodynamics says there's no perpetual motion. So that means that the heat of the sun, the heat source of the sun, cannot be eternal. And the earth, too, the earth has a heat source, too, inside of it. That also cannot be eternal. And even the universe itself, even the entire universe cannot be eternal because of the laws of thermodynamics. So Kelvin dared to ask, how long would these things live? And, can physics tell you anything about this? He thought about it for tens of years. And he went through a lot of possibilities. And the three possibilities that he could think of was first, that the sun burns a fuel that will eventually run out. Now, that's the right answer, but he dismissed that answer as being incorrect because he did not know of a good fuel that could do the job at the time. The alternative he considers that maybe the sun is continuously supplied with energy from an external source. And I'll talk about that in a minute. But the one that he eventually settled on as being the most important is that the sun derives its energy from gravitational contraction. Okay, so first off, let's talk about the fuel. Could the sun be on fire? Could the sun be generating heat because it's on fire? And he thought he knew only of chemical reactions that could make the sun burn. And he thought at the time, why should the sun be made of different stuff than the earth? So the sun must be made of the same stuff as the earth. The fact that the sun is burning must mean that it's just like this big bunch of, big barbecue with basically coal burning. Okay. Today, we know the sun is made out of hydrogen, and you could ask the question, could it be that the hydrogen is burning like fuel? Okay. So here's the one equation. I'm sorry, I can't do business without an equation. I apologize in advance. There's only one equation in this lecture that you need to pay attention to, and it's this one. The total energy available divided by the observed emission rate of energy, the observed emission rate of the sun, should equal the lifetime. So this equation is like if you have a gas tank, you have 14 gallons of gas in your gas tank, you know that the engine has 210 horsepower, and that's the amount of power that it can deliver. And so from the amount of power that it can deliver, you know how long the engine can run. Okay, and your dashboard probably has a computer in it that knows this. And so this equation is the same equation. It says that the sun has a certain amount of energy available, and you calculate what's the, if you could measure what the emission rate is, then you can figure out how long it could live. So if the sun was made entirely out of carbon, out of charcoal briquettes, and he can measure the luminosity, how much visible light comes out of the sun. And from taking that ratio, he got that the age of the sun was 10,000 years. Okay, and 10,000 years, Kelvin knew that's way too short. I've got dinosaurs in the ground that are older than that. He knew that the Earth was much older than 10,000 years, so the sun can't possibly be burning. Okay. So he said, so the next thought he tried, and he kept on this idea for quite some time, was can a constant rain of meteors on the sun maintain the sun's heat? So in other words, it's just like it's raining down rocks falling from the sky, and these rocks land on the sun and go boom, and the potential energy of this falling rock is turned into mechanical, and it just turned into thermal energy as it smashes into the surface. Okay, and he figured out how much mass has to be falling on the sun in order for that to be happening. And then he thought it was reasonable. It's about 1/47th of the Earth's mass would be enough to maintain the luminosity of the sun, he thought. So he thought that would be okay, but then he realized at some point they made a precise measurement of the orbit of Mercury around the sun, and they realized that if there are that many rocks falling on the sun within the orbit of Mercury, that it would mess up the periodicity of the orbit of Mercury. So he ruled out his own theory. And so it can't be that the sun is getting its energy from falling rocks. So at this point, he thought about, well, what about gravitational energy of the sun as a whole? Because you could think of it this way, that a gas consists of atoms that are sort of, and at a certain temperature, the atoms fly around, they bounce around, and the energy of each atom is basically proportional to the temperature of the gas. And there's a very strange symbol appearing on my screen right now. That's an extremely strange symbol. I think it's a caterpillar of some sort. If you draw the other antenna, I can see if it's an ant. Anyways, is there a way to make that stop? So the sun, the outer parts of the sun radiate away heat from their surface layers, and as they radiate away heat, they lose kinetic energy and they start to fall down. And I think I'm getting Zoom bombed. And so as the gas starts to fall down,
that's what it looks like. I am sorry, we're trying to stop it.
Okay, thanks. Thank you so much. So but I share your feelings out there. So you have, as the outer layers, they lose energy as they radiate away heat. And what that means is that they lose kinetic energy and they fall down on top of the other things. And this squeezes down. It squeezes down on the sun, and that compresses it. And as it compresses it, it makes the things bounce into each other and makes the energy, and makes the heat go up. Now, so the contraction of the sun as it sort of falls down heats up the sun. This is what Kelvin realized. And so he could then use Newton's law of gravitation to estimate how much total energy all the mass of the sun had. So he knew that from Newton's law of gravitation. And that gives the total energy that he has. And he could divide this by the observed luminosity. And what he found was that the sun could last 20 million years with that much energy.
Sean, you're muted.
Actually, no, he's not muted because there. We were not hearing you, but the system was. The transcripts were showing it.
I'm sorry. It's really funny that a physicist should be having so much trouble with technology. But the thing is that I'm a theoretical physicist, and if you know about theoretical physicists and technology, then you should. I don't have to say any more, right?
No, I know enough theoretical physicists to know that. In this case, we were trying to get rid of the Zoom bomber, and I don't know that we have, but I've.
I know he's got it. So the total gravitational energy of the sun, you can estimate that, and from that gives you the age of the lifetime of the sun, which is 20 million years. And so what Kelvin said is that this is the maximum age of the sun. Okay. It's Eric Harris. Is that the name of the bomber?
I don't know how to find that.
So let's see. So Kelvin says the maximum age of the sun is 20 million years. Okay, tops. And then he says, well, I think the sun, physics proves that the sun can be no more than 20 million years old. Darwin says that the Earth has to be 300 million years old in order for the world to be denuded by geological forces. And so, somebody has to be wrong. And he clearly, in his paper, he comes after Darwin with his mouth open. So what is the source of why is Kelvin going after Darwin of all people? He's not in that field. And the idea is that it's kind of interesting, right? He felt that the second law of thermodynamics proves that motion is irreversible. It proves that the sun and the earth are not eternal. which must mean that they were formed at some time. Okay. And so he felt that it's impossible to conceive either a beginning or a continuance of life without an overruling creative power. Okay. So he was definitely a religious person. You know, he went to chapel every day, prayed in the morning, and he's clearly a religious person. He felt that what Darwin was saying had to be wrong, and he was coming after him based on his personal beliefs. And you know, so let's just talk at this moment about what was the science that Kelvin was missing. Okay. And what he basically had gotten wrong was that fusion is the real power source of the sun. And this became clear over the course of the 1800s. So it wasn't known when Kelvin was starting his work, but it was slowly becoming clear, you know, that people were beginning to see inside the atom and realize that atoms were real. Dalton proposed the notion of the atom to explain chemical reactions in 1803. Radioactivity was discovered in 1896, and you know, Becquerel and Marie and Pierre Curie and all of these people were working on radioactivity at that time. And Thomson discovered electrons in 1897. Einstein importantly discovered the equation E = mc squared, which is the equivalence of energy and mass. Okay. And then Lord Rutherford finally proved in 1911 that there's an atomic nucleus. Okay. And neutrons and protons were discovered shortly thereafter. At the same time, people realized that the sun was extremely different from the Earth. The composition, the chemical composition of the sun was very different from the Earth. Lockyer measured the spectrum of the light emitted by the sun, and he discovered a new element which would only later be found on the Earth, and that's helium. Okay, helium is named after Helios, the sun god. And in 1920, Arthur Eddington, famous astronomer, realized that the fusion of hydrogen into helium could release enough energy if he applied Einstein's theory of relativity, E = mc squared. And then Cecilia Payne-Gaposchkin did precision studies of the sun. And what she found was that the sun is made of 75% hydrogen and 24% helium, with only traces of other elements. Behind you on the screen, you see solar spectrum. And then eventually in 1938, Hans Bethe came up with the theory of fusion. And from there, people just knew that that fusion was powering the sun. Okay. Now fusion has 1,000 times more energy to the mass than gravitational contraction does, and 7 × 10⁷ times the energy of chemical burning. And so if you use Kelvin's equation, you can get 1,000 times more energy out of the weight of the sun. And this gives you a lifetime of around 10 billion years, which is in the right ballpark of the sun's, what they think sun's expected lifetime will be. Okay. This is Kelvin's own equation. The only thing was that Kelvin had no idea that there was a thing called fusion even possible. So what is fusion? Okay, fusion, you take a low mass nucleus, like hydrogen is lowest mass nucleus, and you combine it to make a nucleus that has a small binding energy. And what you find is that the helium nucleus has slightly less energy than 4 hydrogen nuclei, and that's because It needs that energy to sort of bind it together into this very tightly bound helium nucleus. And that fraction of energy times the speed of light squared gives you, in the most famous equation in history, it shows you how energetic solar fusion can be. So it's much more efficient as fuel. And Kelvin just couldn't have known. So Kelvin made the best conclusion that he could make about the sun's lifetime based on what he knew at the time. He just didn't know about fusion. Now we know that the birth of stars is driven by this Kelvin mechanism. You take a dust cloud in interstellar space, and this dust cloud eventually collapses. And as it collapses and contracts, Kelvin's equations tell you that that energy is turned into the heat of this dust cloud. And then the heat, because most of the stuff in space was found by Payne-Gaposchkin to be hydrogen, it just starts fusing once it gets hot enough. And once it sparks fusion, then the heat, then the thing becomes a proper star. And so Kelvin was right about a lot of things when he was talking about the sun. He also tried to estimate the age of the Earth. And here is where he ran into a bit more trouble. Okay, so he felt that that the Earth is formed like the sun by a collapse of rock, and it gets hot. And he felt that inside should have the temperature of melting rock. And so what he did was he measured the temperature gradient in mines, down in the deepest mines in England. It's hotter than it is on the surface. And then he also measured the thermal conductivity of rock. And from that, he figured out how much heat can be transferred through the crust of the Earth. And based on that, he estimated the age of the Earth to be 20 to 400 million years. So it's like, when you're sitting in a hot car and you turn the engine off, it's going to take some time for heat to be conducted through the windows, through the air, through the windows, out into the outside world as your car cools off. Okay, so the Earth is like a big hot rock that's cooling off. That's what Kelvin says. And from there, he estimates that the age of the Earth should be around 20 to 400 million years. So he got a number for the age of the Earth, which is about the same as the age of the sun. And then, you could see how this works in your mind, right? Ka-ching, you figure, wow, these two different estimates give me the same age. I must be right. Okay, this is how you get into trouble. So in the meantime, Kelvin's own student said, well, I'm sorry, boss, but your estimate of the age of the Earth could be vastly wrong. He said that inside the Earth, it doesn't have to be solid rock. It could be molten rock. And so the surface crust of the Earth could act like styrofoam keeping coffee inside a coffee cup hot. And so from that kind of a calculation, he was able to get an age of the Earth, which is about, billions of years, like 4 billion years is a number that if I try to redo his calculation, I get around 4 billion years. Okay. So Perry said, excuse me, sir, I think you might be wrong. And Perry was no slouch. Perry made the first electric car. So he was like a pretty smart dude, but Kelvin just said, I ignore you. My dumb students can't be smarter than me, right? And so later, when it was discovered that there's radioactive elements in the Earth, it was realized that, basically a lot of the Earth's heat can come from the decay of radioactive elements within the core. And nowadays, they think roughly half of the Earth's heat comes from the radioactive decay inside the core. So his estimate of, not only is his estimate of the sun wrong, but sun's age wrong, but his estimate of the Earth's age is wrong because he didn't know about radioactive decay. And here I have a picture of Marie Curie, and I just love this picture because she looks really disappointed. She just looks like she's so disappointed. I don't think she's disappointed in Kelvin. I just think maybe in those days people had to look serious in pictures and they didn't know what to do. But anyway, so how did the situation persist? What happened was there were 50 years of argument over the age of the Earth and the sun. There was a proxy, because these are proper Victorian gentlemen after all. There was a proxy war between their supporters, their more vocal supporters. And in the meantime, the sciences evolved, okay? First, the geologists decided to use physical tools to measure the age of the Earth. And so the whole idea of physical geology started to take off, basically fueled by Kelvin's insistence. And also evolution-based biology began to take off. Other biologists picked up on Darwin's ideas. And what happened was that Kelvin and just a dwindling number of supporters just kept their heels dug in until finally he died. And here's where we get the picture that we have today of Kelvin the Curmudgeon, okay? While he was a champion of science in the public's eyes, scientists tend to view Kelvin, particularly by the late 1800s, as kind of a relic of the former days. He never fully accepted Maxwell's theory of electromagnetism. He didn't believe in atoms. He denied the importance of radioactivity, and he did a proof. He thought that heavier than air airplanes couldn't fly. Okay, so basically he was just a naysayer, saying nay, and so we just thought of him as like this old irrelevant guy. Okay, but he wasn't irrelevant because there was one of his questions that was remaining to be answered. And it's a really important question. And what is the age of the universe? I mean, just asking that question is a very important thing, especially at that time. At some point around 1929, so this is after poor Kelvin passed on, Hubble discovered, he measured the distance to about 25 different galaxies. And he discovered that the distances, the galaxies that are farther away are moving faster. And what that means, and then he plotted here in this plot, this is Hubble's plot. He showed that the velocity increased linearly with distance. And that became known as Hubble's law. And the slope of that curve is called the Hubble constant, okay? So if you look at what the slope h is, the slope is equal to velocity over distance. And so from distance equals velocity times time, you can figure out that 1 over the Hubble constant is a time. And basically, if the universe starts out real small, and just keeps expanding and expanding and expanding, then eventually, you know, it has to have an age, and that age that you get from Hubble's constant is about 14 billion years. Now, today we have many ways to measure Hubble's constant and the expansion of the universe, and they all kind of converge in an answer which is roughly around 13.798 billion years, more or less, give or take. Okay, so there are still questions about how the exact number, how that comes about, but that's not what we're going to worry about right now. At the time, when people started thinking about what does it mean that the universe is expanding, one of our new heroes appeared. This is George Gamov. He's from Ukraine, and he born in 1904. He was one of the originators of quantum theory. He was one of the first people working on, you know, after Schrodinger invented the Schrodinger equation, and he sort of half killed his cat. Gamov used it to understand processes of radioactivity, and he wrote some of the first papers in which he figured out the process by which fusion powers the sun. Gamov and a German named von Weizsäcker did this in 1937. And he came up with a paper by called The Origin of All Chemical Elements in the Big Bang. And this is a paper by Alpher, Bethe, and Gamov. And he also predicted the cosmic microwave background, which proved the Big Bang theory with Alpher, Gamov, and Hermann. And, you know, so, okay, the joke is out here. I mean, the Alpher was Gamov's graduate student. And they wrote the name Alpha, Beta, and Gamov so that it would sound like the first three letters in the Greek alphabet. Okay. And Beta wasn't on the paper, but it turns out that Beta was the referee of the paper, and he thought the joke was funny, so he left his name on the paper. Okay. This is telling you something about our character here, Gamov. And he also, when he predicted the cosmic microwave background, he wrote the paper with Alpher, Gamov, and Hermann, and he wanted Hermann to change his name to Delta, but he wouldn't go along with it. Okay, so now we're talking about the only part of the lecture where my actual research expertise comes in. Okay, so you know, Gamov invented the idea that all of the elements might have been made in the Big Bang. He came up with the idea, and it's called Big Bang nucleosynthesis, the synthesis of all of the nuclei. And his idea is that basically in the first 15 minutes, all of the particles in the universe, the universe is now spread out over everywhere. But back in the day, everything in the entire universe was squeezed into a little blob. And that blob must have been way hot. Okay. So he said that in that hot blob, the elements may have been made by these nuclear reactions. And this is now accepted to be true, although we know a lot more about the way the Big Bang actually worked now than what he knew back in those times. But you know, so the evidence for the Big Bang, he wanted to see if there was what kind of evidence there was for there being a Big Bang in which all this stuff was created. And And he said, you know, the expansion of the universe is one kind of evidence that there was a Big Bang. Everything is expanding from everything else because there was a one-time event that created everything. He says that the Big Bang fusion creates the chemical elements. This is the alpha, beta, and gamma paper, and also the cosmic microwave radiation, that somehow all the radiation that was trapped in the heat of the Big Bang left a background of electromagnetic radiation, which at this age is now much later. It's much cooler. It's only 3 degrees Kelvin. Okay. So so on the one side, there was Gamov trying to answer Kelvin's question of how old is the universe. And he said the universe is expanding. It was made in a Big Bang that made most of the visible matter. On the other hand, on the other side, there was a scientist called Fred Hoyle, who said, no, wait, it only looks like it's expanding because matter is being created everywhere by quantum fluctuations. And he said, the Big Bang doesn't make all of the elements. Fusion in stars makes all of the elements. That's the difference between Hoyle and Gamov. And so who was Sir Fred Hoyle? Sir Fred Hoyle, if you had a short list of the greatest astrophysicists in history, or at least of the greatest theorists, he's probably the greatest astrophysics theorist in history, might be one of the top 10 greatest astrophysicists in history. He came up with the first theory of the synthesis of elements in stars. His first work is 1946. He perfected it in a paper in collaboration with some other authors in 1957. And then he came up with the steady state theory of the universe, which was in 1948, sort of like, because he didn't really want to believe in the Big Bang, okay? And in fact, you know, and he had a named chair in Cambridge University, and he was knighted in 1972 for his great work in astronomy. But you know, he was also one of these science popularizers. He wrote a science fiction book called A for Andromeda. He was a science popularizer who had a regular science broadcast on the BBC. And here's a picture of him at age 45. He came up with the name of Big Bang Theory because he was trying to make fun of it, okay? And sure enough, now there's even television shows named after it, or were. And so there's the alpha, beta, and gamma paper. And here in this paper, Gamov did a calculation in which he calculated, they had measured the abundance of all of the chemical elements. So here are the abundances of all of the chemical elements known to humanity at the time, plotted as a function of atomic mass. Okay, and what you see is this curve is a curve calculated by the theory of alpha, beta, and gamma. And he calculated using this nice simple equation, that curve. And so to him, he thought, wow, boom. It must be that the Big Bang made all of the elements. And the problem was that there's no stable nucleus at atomic mass 5 or atomic mass 8. So you can't go step by step making one element after another. So the Big Bang can't make elements heavier than basically helium, lithium, and beryllium, and boron makes a little bit of lithium, beryllium, and boron. Mostly it makes up to the elements up to helium. Okay. But he was excited for a while. At the same time, stellar nucleosynthesis is the idea that Hoyle came up with. And Hoyle said that the fusion in red giant stars generates elements from carbon up to iron. And he calculated the relative abundance of all of these elements as they would be generated in this huge paper with Burbage, Fowler, and Hoyle, which is called B squared FH. It's famous paper in the history of astronomy, astrophysics. And then the idea is that when these great big stars explode, they hurl all of these elements out into the universe. And this is where all of the elements come from. It's where all of the carbon and our bodies come from. And this is where Carl Sagan's famous phrase from the good old 70s, that we're all made of star stuff. When he's saying this, he's talking about Fred Hoyle's work, okay? And looking mighty dapper at the same time. And so the synthesis of all the elements in the stars, this is the paper by Burbage, Fowler, and Hoyle. They're posing in this picture here, and they're looking at a train here because apparently Fowler was a big train spotter and something of a fan of locomotives, and so they're giving him this model locomotive. But so the stars, their idea is that the stars build elements heavier than lithium, and they were able to show that there's not in their model there's not enough helium to account for the cosmic abundance, and not enough deuterium by far. So when Gamov saw the paper of Hoyle and he knew about his problem, basically he gave up, and he did it in true Gamov style. He made a joke, and he wrote like a funny poem about how in the beginning God created radiation, and it was without shape and number, and the nucleons were rushing madly over the face of the deep, and then God said, "Let there be mass 2." And he saw that there was deuterium, and it was good, and it continued until he made helium. But then when he looked at it, he said, "Wait a minute, there's no element 5. So this whole thing is wrong. We have to go back, and I'll let Hoyle make." And he said, "Let there be Hoyle." And then there was Hoyle, and God looked at Hoyle, and God told him, "You can make the elements whichever way you feel like you want to." So he made a joke, okay? And, so he kind of realized he was wrong, and he moved on, or at least he figured he was partly right in that the Big Bang made the lightest elements, but then you needed stars to make the rest of the elements. And he kind of realized he was right. This is how to do stuff, how to be a scientist in style. How did Hoyle's steady state universe came up in collaboration with Bondi, Gold, and Hoyle. The three of them were watching a movie, a scary movie, and they come up with the idea, a really scary idea. What if instead of having a Big Bang, the universe just kind of repeats over and over and over again? The universe is basically eternal. And could it be possible the universe is eternal? And they came. And he said that the steady production of new matter in space at a very, very slow rate could possibly make it seem as if the universe is expanding. That was their theory. And it was able to explain Hubble's law for galaxies. He was able to explain, he thought he could explain the synthesis of elements in stars alone. Although there were problems, the theory could not get enough of the light elements. He figured there's just some detail that he doesn't have right. His theory does not have a cosmic microwave background radiation. And his theory would also show that the distant older galaxies would be similar to the nearby galaxies. And so all of that steady state theory came to an end with the discovery of the cosmic microwave background by Penzias and Wilson. Penzias and Wilson were trying to make an antenna for communicating with satellites in the mid-60s. And what they found was that there's noise that they couldn't get rid of. They cleaned the antenna, they cleaned all the bird poop off the antenna, and they found out that they could not get rid of the noise. And so they said, well, it must really be there. The universe must have this noise. What could be making this? And eventually they figured that it could be the cosmic microwave background that was basically predicted by Alpha, Gamov, and Herman. And here's a picture that was made by Alpha and Herman. They're joking around, and here's Gamov coming out of a liquor bottle. This liquor is named after what he called Lem, which is the fluid of the early universe. And there's Alpha and Herman sitting on the side. Okay, Gamov. So how did this all end? Okay, well, eventually Gamov passed away, but there were 50 years of argument over the age of the universe. In the meantime, both astronomy and nuclear physics evolved rapidly. For most, the discovery of the cosmic microwave background killed the steady state model. But Hoyle and a dwindling number of supporters kind of dug in and hung on until the end. And, so why did Hoyle hang on? Why did Hoyle hang on? That's you're asking yourself. Maybe he was just, an old esteemed professor, and maybe just us old esteemed professors, we hang on to our antiquated notions for our entire lives, But what he said was that the reason why scientists like the Big Bang is because they're overshadowed by the book of Genesis. It's deep within the psyche of most scientists to believe in the first pages of Genesis, okay? The Big Bang seems like a creation event. And Hoyle didn't like having a creation event because he was an atheist, and he felt that religion had no place in science, okay? So here's another guy who probably, you could argue, was led astray by his preconceived notions. Didn't face the facts. And so it turns out that the Catholic Church is a big supporter of the Big Bang Theory, right? They're one of the early people who realized that the universe was expanding, and the explanation was an abbot named Lemaitre, and he started a lot. The Vatican has always been supporting astronomy. I mean, I think when they put the thumb screws to Galileo, they kind of got a black eye from that and decided, no, we're not going to do that again. Okay, so they've supported astronomy, and they had a lot of the early meetings on the Big Bang Theory were composed of scientists. Yes, the best scientists in the world working on the subject, but they liked it because they felt that it did reflect that there was creation. Okay. Now, about me, I'm kind of, I tell you, I'm an agnostic about this. I think the good thing about science is that it's true whether you believe in it or not. Here I'm quoting Neil deGrasse Tyson, who is my pope. I'm going to end with that. So thank you for sticking with me for this long talk.
Well, thank you, Dr. Gavin. Really appreciate it. Megan, did you have some questions? Yes. Thank you for the comment about the head of the Vatican Observatory. Yes, I was thinking about Brother Guy.
Yes, he's from Detroit. So there you go.
Whoa!
Yeah, yeah. He went to Detroit Jesuit or whatever the high school is.
Yes, I think it was Jesuit, that Detroit Jesuit at the time.
Yeah, so he comes back from time to time. So
You're absolutely right.
We haven't had any questions in the chat so far. So if anybody has any, but I've been trying to post links, Sean, just to biographies of some of the people you've been mentioning.
You've posted some very useful links.
And a clarification, in case anyone didn't know Schrodinger's cat, to just let them know no cats were harmed by Schrodinger.
No, you just think about whether the cat is harmed or not.
That's right. So
yeah, sorry about that. I have also a set of papers that I've followed from. You know, there's the book that I read was this Degrees Kelvin by Lindley, and there's also a book called Brilliant Blunders by Mario Livio, and there's a recent biography called Flashes of Creation of Fred Hoyle, and it talks about the debate between Gamov and Hoyle at great length. So there's a lot of stuff out there. If you're interested in this, there's a lot of interest in all of this, because it's sort of, you know, we're still wondering about dark matter and dark energy and how fast the universe is really expanding. And these questions are still at the cutting edge of science.
Well, thank you. I can't believe there are no questions. I guess everyone is too stunned by the massive knowledge. I love the alpha, beta, and gamma.
Yeah, that was funny.
I would have roped someone in on that too.
I also noticed, Sean, when you said that Lord Kelvin became a knight at 42. Maybe that's where Douglas Adams got his 42 from. That's what I was wondering.
Possible. That's quite possible. I tried to write a paper. My thesis advisor was named Bain, and I tried to write a paper with a guy named Kirch, and we wanted to call it. We were calling it KGB, and so we put Bain's name on the paper in order to get it to be KGB. And then he had to put his thesis advisor on it. It became KGBW, and that kind of screwed it up. But, you know, that was during the 80s, though. So,
yeah,
pretty much date that.
That's funny.
Yep.
Yes, Ellen is saying that the Webb telescope is showing some challenges to the standard model lately.
Always.
In the chat. Yes. Oh, yes. There will always be new ways of looking at things. And it's the people that dig in their heels that are a problem.
Right. The whole question of how you measure the expansion has evolved quite a lot since, you know, 1920s, you know, and people have realized that we don't even know what most of the universe is made out of. Most of the universe is stuff that we don't see, called dark matter. And there's this dark energy that's also present that somehow forces the universe to expand. There's a lot of evidence of dark matter. You could see that it works by gravity, pulls all of the stuff around it. You could see the orbits of stars orbiting around dark matter and things like that. But dark energy is revealed only through the expansion. And so people are trying to measure that very carefully. And it's one of the new things that people are really excited about. And, you know, it's really it's really heck to go from the days of Kelvin where you thought you understood everything that you saw, and now we feel like we don't understand just almost most of everything because we can't see it.
Hey, Sean, we've got another question for you.
All righty.
If the universe is constantly expanding, why do galaxies occasionally collide?
There's a lot of, the expansion is only on average, okay? So you have all kinds of orbits that are taking place, like the Earth is orbiting around the sun. The sun and the Earth together are orbiting around the center of the galaxy in this kind of whirlpool. And this is all, everything is attracted to everything else by gravity. So if two things come together, if they go randomly moving, everything is moving apart from everything else, but they all have like a velocity also from just their motion. And they end up like things moving past each other. They end up moving past each other. They fall into their gravitational wells, kind of come together and collide. So, you know, we're in a local group, local cluster of Virgo cluster, in which our galaxy and the Andromeda galaxy are sort of orbiting around each other. And about 1 billion years from now, the Andromeda galaxy is going to hit our galaxy. And, you know, I think that'd be really cool to see. And I don't know how long we would last. You know, I guess it depends on if we're in the path of something. Does that answer your question?
I think that does. I'm going to look for, there's a good video model of the Andromeda merger with our galaxy, with the Milky Way, that I've seen on YouTube. So I'm going to see if I can find that.
Are there any more questions?
There's lots of thanks to you in the chat, Sean.
Yes.
So people really enjoyed it.
Well, I'll take it. You know, it was
a lot of fun.
I always enjoyed talking, and talking is one of my favorite things. You know, I've gone into the talking business as a professor, and so I do like the sound of my own voice. And so I appreciate you giving me this opportunity to exercise.
Well, we're happy to give you the opportunity, and thank you to everyone else who came. We will be starting up programs again. I don't know how to read that, Matt. We'll be starting up programs again in January, but we haven't set the schedule yet. So keep an eye out. It will be announced on the DPL website. Megan will announce it. You're welcome, Matt. We will be setting the schedule, and so it will be on Eventbrite. It will be on the DPL website. Megan will be announcing it. So thank you for joining us, and all the best holidays to everyone.
Bye all.
Thanks a lot. Bye-bye.
Goodbye. Thank you. I've got a question about a transcript. We do not have transcripts available, but the recording will be available. I'm going to send it to everyone on the YouTube channel in a couple of weeks. It takes a while for marketing to get it up. Okay, thank you for joining us.